This is the title of my talk, Minimal Spheres in Ellipsoids. This is my buddy, Renato, whom I worked with on this problem. This is my university, date, this is my institute and my sponsors, okay? So, let me give you, just as a launch to the problem, let me give you the basic ingredients of this talk. Suppose you have an n-dimensional Riemannian manifolds and you take a hypersurface sigma, then you take a family of diffeomorphism, a one-parameter family of diffeomorphisms of your manifold, phi depending on t, and you consider the following variation of sigma. You take phi t applied to sigma. This is another hypersurface. You compute the area of this and take the derivative at t equals 0. And this gives the following integral here. This is the integral of the inner product between the mean curvature vector of sigma and the variational vector field associated with this flow, okay? So this means that if sigma is minimum with respect to, if it's a minimum point for the area functional, then the derivative is 0 for every variational vector field v, and that implies easily that the mean curvature vector has to be 0. So sigma minimal is the same as requiring that the mean curvature is 0. So particular cases, if you take a two-dimensional manifold M and a one-dimensional minimal hypersurface, that would be just a curve, and it's a geodesic, of course. But the case we're interested in this talk is when the ambient manifold has dimension 3 and sigma is homeomorphic to a sphere, S2, and so we'll talk about minimal 2 sphere, okay? One thing to keep in mind is that there is this theorem by Franco that says that if you have any manifold with positive Ricci curvature, which then any two minimal hypersurfaces must intersect, okay? Let me also specify that all the minimal 2 spheres will be meant to be smooth and embedded, okay? Not immersed, but embedded. All right. If you want to think about some minimal spheres, don't think in Euclidean space. Minimal spheres do not exist in R3. In fact, in R3, there are no minimal compact surface without boundary. So if you look on Google, you look at minimal spheres, you will find some examples. Here it also says minimal sphere, but it's a fake thing, okay? They don't exist in R3. But they do exist. Minimal 2 spheres exist in 3 spheres. And the 3 spheres we'll be interested in this talk are ellipsoids. So an ellipsoid is a 3-dimensional object that lives inside R4. If you fix 4 positive numbers, A, B, C, and D, then you can take the set of points of R4 whose coordinates satisfy this equation here. So this is a 3-dimensional ellipsoid with the axis A, B, C, and D, okay? Of course, this is diffeomorphic to S3. And there are 4 easily seen minimal 2 spheres, which are planar. They are obtained by taking the intersection of the ellipsoid with the 4 coordinate planes, okay? So of course this picture is in 1 dimension less than it should be, right? But just to give you an idea, this would be the 3-dimensional ellipsoid, and these are the, well, 4 planar 2 spheres, okay, obtained by taking intersection with these planes. Why are they minimal? Because they are in fact totally geodesic, because they are fixed points of isometries of the ellipsoid. That is, there are some, changing the sign of one of the variables is an isometry that preserves the ellipsoid. And these spheres are exactly the fixed points of this isometry. So they are more than minimal. They have identically 0 second fundamental form. That is, in particular, that implies mean curvature equal to 0. Okay. So in the standard ellipsoid, you have at least these 4 minimal 2 spheres. Okay, they're in a sense trivial. There's a famous question of Yao in 1987, asking whether all the minimal 2 spheres in ellipsoids are planar. That is, if these are the only minimal spheres that you can find in ellipsoids. Okay. And let me say that, okay, probably I should make a comment on this. You should expect that generically, inside a 3-dimensional sphere, you would find 4 non-trivial minimal 2 spheres. There's a topological argument for this, which is the set of all embeddings of a 2-dimensional sphere inside a 3-dimensional sphere has the homotopy type of a projective space, in fact, of RP5. I'm sorry, of RP4, in fact. And RP4 has a topological invariant called the Lusternicke-Schneiderman category, which is equal to 5. And you would expect that on a manifold with category 5, any smooth function would have at least 5 critical points. Okay. But now keep in mind that constant functions, like a constant map from S2 to S3, this also minimizes area in some trivial sense. So this has to be considered like a trivial critical point of the area functional. So there's 4 remaining non-trivial minimal 2 spheres. So you would expect in general that in a 3-dimensional sphere you would find at least 4 minimal 2 spheres. Okay. So in particular, the question of Yao was whether the ellipsoids actually minimize the number of possible minimal 2 spheres. Okay, in 1966, Almgren proved that the conjecture of Yao is in fact true if all the axes of the ellipsoid are the same. So if you take a round 3 sphere, the only minimal 2 spheres are equators, okay? Intersection with their planars. And then in 2017, Brian White proved, in fact, that this remains true if the ellipsoid is not too different from a round sphere. That is, if the coefficients, if the value of the semi-axis A, B, and C and D are sufficiently close to each other. Okay. But now what attracted our attention was a recent paper by Haslhofer and Ketover in 2019, where they proved that if you fix B, C, and D, and you take A sufficiently large, so you get this kind of ellipsoid here, then there is at least one non-planar minimal 2 sphere. Okay. In the picture, this is given by this yellow curve, which here in the 2-dimensional picture sort of self-intersects. Okay, which is not the case for the minimal sphere found by Ketover and Haslhofer. They found a true embedded minimal 2 sphere, and they use minimax theory, which is very fashionable, right? Minimax theory and the mean curvature flow, probably. So it's a very sophisticated proof that Renato and I were looking at, and we found some ingredients that could that suggested that maybe a more general result could hold, like a better estimate on the number of minimal two spheres could be found. So, okay, yeah, this is the description of the paper by Haslhofer and Ketover. So if A is much larger than B, C, and D, then there is at least one minimal two sphere, sigma HK, from these two names. It's found using minimax theory and the mean curvature flow. Then it has a property, technical property that I may discuss later. And its area is between the area of the of this large minimal sphere here and 2 times the area of this minimal sphere, which is here, okay? And in fact, when A goes to infinity, this minimal two sphere converges to this sphere with multiplicity 2.
Paolo, can I just, I think there may be a typo, because right, the extreme areas, they're here for the same sphere. They're both by 1. You probably mean.
I'm sorry. This is one of them, and this is the other one.
Okay. Sorry to interrupt, but it's not a typo. I think you just circled the wrong sphere. So it's actually between once and twice the area of the same pi 1. Pi 1 is the middle one.
Oh, I'm sorry. I'm sorry.
The points are correct.
Yeah. My confusion is in fact. Yeah, that's right. We haven't checked this very carefully, but apparently this this new new minimal spheres has the area which is it's bounded by its area is bounded by the area of this and twice the area of the same thing. Sorry. Probably this appears when A is such that the area of this is exactly twice the area of this. That's why I got confused. Sorry.
Sorry, they only say A is big enough, or they give some number for A?
No, they don't estimate A. Or they just say that it's for large A. But we have an idea of how to estimate this A. Maybe this will.
That's important. Yeah. Okay. Thanks.
Yeah. So the result that Renato and I managed to prove based on these ideas is the following. Okay, we have to restrict the family of ellipsoids that we consider. That is, we take 2 of the semi-axis equal. So either B equal to C or C equal to D. Okay. So in this case, we have an ellipsoid which is invariant by revolution. Okay. So it's a rotationally invariant ellipsoid. And in this situation, we prove that as A goes to infinity, the number of non-planar minimal two spheres in the ellipsoid goes to infinity, in fact. There's not only one, but you can find infinitely many of them. Well, you can find an arbitrarily large number of them as A goes to infinity. Okay. So this is our result. Observe that we have this extra assumption which is not present in Haslhofer and Ketover paper. They prove the existence of at least one for any value of B, C, and D. All right. Let me say that one of the main features of the problem is exactly the problem of symmetries. If you take an arbitrary ellipsoid with possibly pairwise distinct semi-axis, then its isometry group is just a product of 4 copies of Z2. That is, you only have the reflection around the coordinate axis, okay? Whereas if you take 2 of the semi-axes equal to each other, then you gain extra symmetry by taking an entire O2. There are not only reflection around the planes, the axis, but also you have a rotation around in the plane generated by two of these four coordinates. Okay. So our minimal two spheres, in fact, will be invariant by this action of O2, and also invariant by reflection around this plane here. Okay. And also we found this, all these minimal spheres will have will intersect the other planar minimal two spheres, which are also invariant by the same action. Okay. And well, of course, we know that this is true in general. Any two minimal spheres in the ellipsoid will intersect each other because of the Frankel theorem. But in this situation, we in fact can count the number of intersections that each one of these minimal sphere has with the only other planar minimal two sphere, which is invariant by the same symmetry. Okay. All right. This is an idea. Okay, this is more or less the framework for the proof of this result. It has 4 steps indicated here on the left, which are as follows. Okay, first we use a reduction to a lower dimensional problem using a result by Xiang and Lawson that exploits this, the existence of these symmetries. That is, minimal two spheres that are invariant with respect to this group of symmetries, they become geodesics in the orbit space of this group action. Geodesics with respect to a metric which is not exactly the induced metric by the isometric action, but a conformal multiple of that metric. Okay, we'll discuss this at some point later on. So first, we reduce the problem from finding minimal two spheres to finding free boundary geodesics in a manifold with boundary. Then we study the geodesics in this manifold with boundary. And here the crucial observation is that the boundary of this manifold, in fact, is singular. That is, the metric degenerates on this singular boundary, and that creates many difficulties for the existence of geodesics starting from the boundary of this manifold. So for this, we use, in fact, some existence theory for the plateau problem, and I will tell you exactly how this is done. And once the existence, a local existence problem is solved, then we use some more standard variational theory to determine which of these geodesics, in fact, induce minimal spheres in the ellipsoids. So once we have this variational characterization, we use bifurcation theory for this problem, in which the bifurcation parameter will be, of course, the length of the semi-axis of the ellipsoid that goes to infinity. And so this requires the study of a singular Jacobi equation along this singular geodesic. So we do an analysis of this singular Sturm-Liouville equation. And with this, we get existence of infinitely many bifurcation points, which still doesn't conclude the result, because the last step we need is that we need to prove that all the bifurcating branches persist for every value of A going to infinity. So For this reason, for this purpose, we used some global bifurcation result of Rabinowitz, which requires a method for to make sure that bifurcation branches don't just terminate at some point. Okay, so I will discuss this in the rest of this talk. So once these four steps are taken into account, then the proof of the result that I've given you is finished. Okay, let's start with this problem of reduction to a geodesic problem. The general theory is as follows. Suppose that you have a Riemannian manifold with an isometric action of some group, okay? Say a Lie group, a compact Lie group. And then you have, of course, M over G is the space of orbits of this action. You have a projection. And there's an open dense subset which consists of points whose orbit is principal. And the projection restricted to this principal part onto its image is in fact a Riemannian submersion, okay? But there are some singularities in general in this quotient, which are precisely the points whose whose orbit is not principal, okay? Okay, then you consider on the quotient of the principal part of M by the group G, the function that assigns to each point the volume of its orbit. Well, I'm sorry, the volume of the corresponding orbit, that is of pi inverse of x, okay? This is a smooth function on this open set, and it extends to a continuous function on the boundary, being 0 on the boundary, okay? So you have this volume function, which is smooth and positive in the interior of this quotient, and 0 on the boundary. And so the Sung-Lawson result is that if you have a hypersurface in M, which is minimal, and it's G invariant, then its projection is also minimal on the quotient when the quotient is given this metric here. So this is the quotient metric times the volume function raised to the power 2 over k, where k is the codimension of the principal orbits, okay? Observe again that this metric here is singular on the boundary because the function v is 0 on the boundary of this set. So in our setting, the Riemannian manifold is the ellipsoid, so it's a sphere with this metric, and the group is O2, acting on these two variables. The orbit of a point x is given by this circle here. So the orbit of almost every point is a circle, except clearly for the points that are fixed, that is the points where these coordinates x2 and x3 are equal to 0. So this is like an equator of this ellipsoid, right? So the principal part of this action is everything that is above of this equator. The principal part, I'm sorry, is the entire ellipsoid minus this equator. I'm sorry. Now the quotient, this is now a two-dimensional object. So you have a three-dimensional manifold and you have a one-dimensional group acting on it. The quotient is this two-dimensional manifold, which is in fact diffeomorphic to the upper part of this ellipsoid. Now this is really an ellipsoid in R3, okay? This is the ellipsoid given by this equation here. So basically, you have killed, like these two variables, x2 and x3, become just one single variable, okay, in this quotient. And it suffices to take, of course, R positive. So you take only the upper part of this ellipsoid here. And the boundary of this half ellipsoid, which is an ellipse, a real ellipse, is the singular boundary for the Siang and Lawson metric, okay? The volume function is simply the length of a circle which has radius given by b times this number. And so the quotient of S3 with the group G is identified with this upper part of the ellipsoid in R3 with metric given by this function times the ellipsoid metric. Okay. And also, it is not hard to prove that if you want to have a G2 invariant, G invariant minimal 2 sphere that projects to a geodesic on this ellipsoid, which starts orthogonally from the boundary and arrives also orthogonally on the boundary, okay? But please keep in mind that the boundary of this object is singular. So our problem becomes find free boundary geodesics in an ellipsoid with singular boundary. That's what the problem boils down to. So let's imagine now that we can project this ellipsoid on the plane and have a real ellipse, okay? But keep in mind that the metric is non-flat here. The metric is the conformal metric obtained by multiplying the metric of the ellipsoid here times this function, okay? But in any case, we have this ellipse with this boundary, which is singular. And we can parameterize this half ellipse here. Well, actually, the entire ellipse with this map, alpha of S is A times the cosine of S, D times the sine of S. D is the value of this. These are the two semi-axes. This is D and this is A. There's no B here. This has been projected down, okay? And so this is the point alpha of 0, alpha pi over 2, okay? And also observe that, okay, this metric here is symmetric with respect to reflection around this axis and also around this axis, okay? So in particular, this is a geodesic. This is a free boundary geodesic, and this corresponds to one of the two planar spheres, to one of the four planar two spheres on the ellipsoid. And also this, for the same reason, this is also a free boundary geodesic, which corresponds to another minimal two sphere on the ellipsoid upstairs. So what we want is really now new geodesic that start orthogonally from here and arrive orthogonally at some other point. Maybe going like this, maybe going like this. Or maybe like this. Okay, so the first problem is dealing with the fact that the metric is singular here on the boundary, okay?
Can I ask a question?
Sure.
So what if the geodesic does not start orthogonally but just transversely? Do you obtain some?
This kind of objects would give singular minimal spheres on the ellipsoid upstairs.
Okay.
But as a matter of fact, we can prove that there are no in this singular ellipse, the only geodesics that manage to arrive to the boundary must arrive orthogonally. So there is no way that you can get a geodesics that arrives on the boundary and not orthogonally in this singular metric.
Okay, thank you.
Okay. Yeah, but that's a good point. So, and this is a very tricky problem, like determining these free boundary geodesics when the metric is singular. And we have managed to prove the following theorem, which says that starting from any point on the boundary, in fact, there is a unique orthogonal geodesics issuing from this point, okay? And so there is a unique one, and so for instance, you never have two orthogonal geodesics that separate at some point, okay? Observe that this is a local result, but in fact, as soon as you are inside the ellipse, then this becomes a regular Riemannian manifold. So you can extend this geodesic, and as long as it remains inside the ellipse, it can be extended. The only problem is when it becomes again close to the boundary. Okay. So, but in any case, there exists a unique maximal in the sense of a maximal definition of this geodesic, starting orthogonally from every point of the boundary. And I want to discuss this proof with you because this is not made by hard analysis, as we tried for several months, in fact. This is made with a very subtle trick, which uses something which in principle is even a harder problem, which is the existence of solution for the plateau problem in the ellipsoid. And it's based on the following argument. Okay, you take a point which is sufficiently close. Okay, you have this ellipse. You take a point which is very close to the boundary of this set. Okay, so its orbit in the ellipsoid. This is a circle because this is not a point in the boundary. So this is a regular orbit. It's a circle. And if this point is very close to the boundary, then this circle is small, okay? And so you have existence, a uniqueness of a minimal disk, which is bounded by this circle in the ellipsoid, okay? Call this disk dx, okay? Now this disk is unique. It is smooth because we're in dimension 3, right? It's a minimal surface in dimension 3. It's embedded, and it's also invariant by the action of G, okay? And for this invariance means that it's union of orbits, and this implies that there must be one of the orbits that composes this disk has to be a fixed point. Because, of course, if you have a disk which is foliated by circles, there must be just a trivial one, right? A point. So that this disk is a minimal object in the ellipsoid, which is projected to a geodesic when it's projected on the quotient space, and that must touch the boundary because it has this it contains this fixed point. Okay. I don't remember exactly why this geodesic has to be orthogonal. Can you remind me, Renato, what is the argument to prove that such a geodesic has to be orthogonal to the boundary?
Well, in the proof, the way that it's written there, you're actually proving just the existence of orthogonal ones. You're not discussing why transverse ones don't exist. So,
okay, well, right. Okay, yeah, and so this geodesic that comes from the solution of the plateau problem with given boundary. This gives, in fact, a small local orthogonal free boundary geodesic starting from a point on the boundary. Okay. Uniqueness comes from the maximum principle also. Okay. So there is behind this, there is a quite involved geometric setup to prove this theorem. It's not by brute force as we expected at the beginning, because you see, this is really a two-dimensional problem, and you have to solve like a second order linear or ODE, right? And so you may think that this would be a piece of cake. But this singularity problem is really hard to deal with, and this is the way we actually managed to solve the problem, not by solving ODEs.
Paulo, since I interrupted you already, maybe I should also just add that that's inspired by this paper of Haas, Norburi, and Rubinstein, right? They have a similar kind of idea, so we adapted that to that case. I wouldn't claim too much originality. Haas, Norburi, and Rubinstein kind of came up with that strategy.
Okay, very good. Thank you. Okay, so we have, starting from each point, a geodesic, which then enters and then does something that we don't know what it does, okay? And we want to find those that not only start orthogonally, but also arrive at some other point, okay? So our idea is the following. First of all, as I told you, since this metric is invariant by reflection around this line here and also reflection around this line here, then these two are geodesics, okay? These two segments here are true geodesics. And we refer to this as the horizontal orthogonal geodesic, and this is the vertical one, okay? These are the ones we're not interested in because, as I told you, this lift to planar minimal two spheres on the ellipsoid. So these are not the good ones. So we consider the following. Okay, we start orthogonally from here, and we look for geodesics that say arrive orthogonally onto this vertical one. Okay. Once we have a geodesic which starts orthogonally and arrives orthogonally here, observe now that this is non-singular, this part here. Then we can reflect this and obtain another, an extension of this geodesic, which is now orthogonal on both sides, okay? So rather than having singularities on the two endpoints, we just have a singularity on one endpoint and a real orthogonality with this vertical geodesic here, okay? So this is our strategy. This is also, by the way, yeah, this method of reducing dimension was used by, as I told you, by Xiang to also give counterexamples to the spherical Bernstein problem on the sphere. That is, he proved existence of minimal spheres which are not equators on round spheres using this method. Okay. We have an argument to show that these geodesics that start orthogonally from the boundary, they never they don't have self-intersections. And that is basically a continuity argument, considering the fact that this one doesn't have self-intersection and this one doesn't have self-intersection either. So it's like a continuity argument in this sense. And also, it's not hard to prove that any such geodesic must intersect this vertical one always transversally. That is another point that we have. So starting from every point of the boundary, there is a first instant at which this geodesic hits the vertical geodesic, okay? And remember that we want to find those geodesics that arrive orthogonally. So what we do is we define tau of S is exactly the first instant at which this geodesic intercept is vertical geodesic, okay? So this is the point alpha of S. This is geodesic gamma of S. And this is the point gamma of S at the instant tau S, okay? So we take a function that depends on two variables. A is the length of the axis, and S that gives the point on the boundary. So we take the geodesic gamma S, we compute it at the instant tau of S. We take the inner product of the tangent vector here with the vertical vector, okay? And then it's clear that we have an orthogonal geodesic if this function is equal to 0, right? So this function equals 0 means that this geodesic arrives orthogonally. So the solution of our problem, now the embedded minimal two spheres correspond to the zeros of this function here. A is the value of the axis, and S is the point on the boundary of this ellipse from which this geodesic starts, okay? So we have a function of two variables, which is defined in this stripe. So A is positive, and S is between minus pi over 2 and pi over 2. So we have a function defined here, and we want to find its zeros. Now it's somewhat more concrete problem, right? So what we prove is that the zeros of this function are exactly like this picture here. So they form infinitely many, say, continuous paths that go to infinity on both ends, okay? So this means that if you fix A here, the number of minimal two spheres corresponding to that ellipsoid is exactly the number of intersection of this zero set with this vertical line. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? In this picture, corresponding to this A, there's 12 minimal two spheres. So if A is large enough, you obtain as many as you want, okay? So basically now the problem is showing that the zero set of this function has this shape here, okay? And this is now this becomes like almost a classical bifurcation problem. So we're more or less at this point here. We have reduced the problem of minimal two spheres to a bifurcation problem for a function of two variables, okay? And so now we use standard bifurcation results let me see, okay. The most famous one is this one by Krondal and Rabinowitz that basically tells you the following thing. So suppose you have a function of two variables, A and S, and suppose that this function is 0 for when computed at the point A0, which is like, okay, this line here corresponds to all these horizontal geodesics for all different values of the parameter A, okay? So each one of the point here corresponds to this geodesic at the corresponding value of A. So we have our function is 0 on all pairs of the type A0, okay? Note that this point here corresponds to S equals 0. So we have this. Suppose that you have that at some instant A, the derivative of this function with respect to S is 0, but that the second derivative with respect to A and S is non-zero. This is like this is a degeneracy condition, and this is a transversality condition that are the two basic assumptions for bifurcation. Then, so if this is A star, then the set of solution of the equation near this point consists of the trivial branch, this, plus another smooth curve that intersects transversally this trivial branch, okay? So every time you satisfy these two assumptions, you have a local bifurcation branch for your problem, okay? Clearly, this one here leads to the study of a linearized problem. Observe that taking the derivative with respect to S means that we're taking, so we have this geodesic starting at different points, that we take the derivative of these geodesics, and so we have a Jacobi equation, right? So this equation here becomes a Jacobi equation.
So sorry, S equal to 0 corresponds to which points? The beginning of the horizontal line, is that it?
This.
Or
this is S equals 0.
Thank you, thank you.
And the unique geodesic, the unique orthogonal geodesic that start from this point is always orthogonal here.
Okay.
So this means that f of the A0 is always equal to 0.
Mm-hmm. Okay, thank you.
Yeah. And so to study the this is the linearized equation. We have to linearize the equation of the geodesic, but we only have, the good point is that the equation of the geodesic is a big mess, but it's easy to linearize along this equation here. So this becomes a nice, more Sturm equation, but again, it's singular, okay? So it has the singularity at the initial point. This slide here explains more or less how the Jacobi equation is used to determine the partial derivative of f with respect to s. But it's pretty obvious, that is, taking variation of s means taking a variation of geodesic, which is given by this field here. So this value here is simply the value of the Jacobi field corresponding to this variation of geodesics, the value of its derivative at the point 1, which now corresponds to the point of intersection of the geodesic with this vertical one, okay? We have reparametrized everything so that the arrival time is equal to 1. So now we basically have to study a Jacobi equation which is singular at the initial point, and then the final boundary condition that we want is that the derivative has to be 0, basically, okay? The transversality condition requires to compute the derivative of this object here, which is also computed easily, because now at this point, at the point 1, there's no more singularity here, okay? So the Sturm-Liouville problem that we get is something of this form. So it's like PV prime prime plus QV with, this is the initial condition that gives the orthogonality from the boundary. So it's a mixed condition that involves both the value and the derivative of the function, as you would expect, right? Like the boundary condition for Jacobi fields of free boundary geodesics involves the derivative of the Jacobi field at the beginning, and also the value of the Jacobi fields and the second fundamental form of the boundary, sort of. So this information is in this boundary condition here. The thing is that the coefficient P, which is usually positive, now has this form here, and at 0, this is 0. You see, there's this T here, which makes it 0, and which complicates things. But these are relatively easy, because now this is a linear equation. This function are real analytic, and you would expect solution in power series. And in fact, you determine easily that there exists exactly, okay, that this equation here has exactly one real analytic solution at 0. And this unique real analytic solution satisfies this initial condition here. Unique up to multiples, of course. So with this, you treat this singular problem exactly like a regular Sturm-Liouville equation. Once you settle this regularity problem that comes from this classical method Frobenius, you just use power series to resolve this equation here. Okay, and then maybe I should go a little faster. So we have the corresponding eigenvalue equation, which is this. This is the initial condition that we have, and this is the final condition that we want. So this is an eigenvalue problem, and again, we prove that there exists an infinite sequence an for which this going to infinity, for which this problem admits 0. Lambda equals 0 as an eigenvalue. So this means that for all these values of an is satisfied the first assumption in the Rabinowitz and Crandall bifurcation theorem. So this is the degeneracy assumption for the Crandall and Rabinowitz theorem. And then we also prove that the derivative of the nth eigenvalue at the point where it becomes 0 is always negative. And this is basically the transversality assumption in the Crandall-Rabinowitz theorem. So lambda equals 0 in eigenvalue, and the lambda prime of 0 different from 0, this for some value of a, this gives bifurcation at a. And we determine infinitely many bifurcation points. So that's the first problem. And this is what I've just explained. So this is the degeneracy condition, and this is the transversality condition given in the theorem. So to prove the existence of infinitely many bifurcation points, basically we compute the Morse index of the trivial geodesic, and it's very easy to show that as a goes to infinity, the Morse index has to go to infinity, and this implies that the corresponding Jacobi equation must have 0 eigenvalue infinitely many times, okay? Because jumps of the Morse index must correspond to determine zeros of eigenvalues. Okay, now let me tell you briefly about the global bifurcation argument here. There is a theorem by Rabinowitz that says that under a certain properness assumption, then the bifurcating branches for the equation are either non-compact or they must reattach at the trivial branch. So if you take a bifurcation branch, this bifurcation branch is either non-compact or at some point it has to go back to the bifurcation, to the trivial bifurcation branch. This uses an assumption which is the properness of the map F. Well, actually, no, I'm sorry. You need properness of the projection function, like from R2, you project onto this line here, and you restrict this projection to the 0 set of this function, and this has to be a proper function. Basically, this means that for each value of a, the set of minimal spheres corresponding to that a is compact. And that is also a classical result that if you are in dimension 3 with positive Ricci curvature, then the space of minimal spheres, the space of minimal submanifolds is compact. Okay, so this is the properness assumption that you need for this global bifurcation result of Rabinowitz. Also, okay, so what happened is that we also proved that these bifurcation branches cannot, for every A, we must stay away from pi over 2 and minus pi over 2, okay? So what happens with this bifurcation branch when they go to infinity? They cannot go to infinity here because it has to stay away from here. It cannot go to, okay, we need an argument to show that it cannot go to infinity here, okay? And this is the fact that for every fixed value of A, there's at most a finite number of branches that can go back here, okay? So maybe there will be a finite number of them going this way, but then infinitely many will not be able to go to infinity in this direction here. So either they go to infinity in that direction, which is what we want, or they must be at some point, they must reconnect with the trivial branch here, okay? And we managed to rule out this possibility here. It is never the case that a bifurcating branch starts from here and then it ends at some other bifurcation point. And the way we exclude this case, let me see, is because
Paulo,
yeah.
Just real quick, we may have to manage the time though.
Yeah, let me try and finish in 2 minutes then. All the geodesics in these bifurcating branches, they have a fixed number of intersection with the horizontal geodesic. So every bifurcating branch is characterized by geodesics that have a fixed number of intersections of this point, okay? And this number of intersection is strictly increasing on this point. So you cannot have the situation where a bifurcating branch starts from here and then it finishes at another bifurcation points, because the bifurcation point issuing from this point contains geodesics that have a certain number of intersection with the horizontal one, but the geodesics in this bifurcation point must have a larger number of intersections. So this is never the case. In fact, it's never the case that two bifurcation points intersect at any point, okay? So this is our final argument. There is this invariant, which is number of intersection with the horizontal geodesic. And observe that this means that the corresponding minimal spheres also intersect these elongated planar spheres at a fixed number of orbits of the action, okay? So with this, we exclude the possibility that the bifurcation branch, so we know that the bifurcation branches are non-compact, and maybe a few of them will go this way, but infinitely many of them have to go in the other direction. And so this is what we wanted for our multiplicity result, right? So this finishes the proof. And in fact, very recently, we managed to prove a little more, that is, that in fact, all these bifurcation branches have to go to infinity in a sense. And also we managed some kind of description of what is the limit of these bifurcating branches at the end, because as you can imagine, when the value of this half-axis goes to infinity, then this ellipsoid tends to a cylinder, to the product of an S2 times R, okay? And so these minimal two spheres have to go to minimal objects also in the cylinder, okay? But minimal submanifolds of the cylinder are studied, okay? And there's this paper by Harold Rosenberg that describes these geodesics, and basically what they are either just simple slices of the product, okay? And there are also some onduloid type minimal spheres. And we can exclude that the limit are onduloids. So this means that all these minimal two spheres that we find, in fact, they tend to accumulate around these planar minimal spheres here. So our conjecture is that at the limit, as A go to infinity, these branches converge to these planar minimal spheres with multiplicity equal to the number of intersection, of course, with this. So that this number of intersections is, in fact, gives the multiplicity of the limit in each one of these branches. Okay, I think this is all I wanted to tell you. So thank you very much for the attention.
All right, thank you. I think we have time for one question, so no need to raise hands. Let me just point you towards the fact that now Google Meet allows you to raise your hand officially, just at the bottom of the interface, but you don't have to do that. You can just ask the questions out loud. So the talk, yeah, go ahead, Daniel.
At the beginning, you spoke about the Louis, I can never say that name, Louis Schneiderman category, right, of the embeddings of
yes.
S2. Yeah. So is a standard? I mean, is there a Louis Schneiderman category for every space of embeddings? I mean.
Yeah, but this is just a suggestion, because if you want to implement Louis-Schneiderman theory, you need to have a lot of properties like Palais-Mer condition and things like that, that usually doesn't work for the area functional. So really, it's just an idea of why one would expect, say, 4 minimal spheres inside a 3 sphere.
Okay, so that's not so that's not standard. I mean, because I mean the idea. I mean, thank you. I mean, but that's not standard. I mean, people at global analysis don't use that type of argument. You mean, or they do?
They do when the functional involved satisfies Palais-Mer, which is not the case here.
Okay, cool. Thank you. Okay.
Yeah.
Okay. Any more questions or comments? Well, if not, let me make a final announcement. So if you are late, next week on Friday, we're going to have Simon Salomon telling us about Lie groups and special holonomy, and that will be the final session of the year. So if you've followed the seminar all year, that will be our official closing ceremony. Please do show up. And in the meantime, let's thank Paulo again, please.